If the ancient Greeks were more accepting towards the idea of infinity, there would not be any debate between who discovered calculus, as it would probably be the ancient Greek mathematician Archimedes, who was born 2 millennia before both Newton and Leibniz. This is because his development of the method of exhaustion was a quintessential precursor to modern-day calculus. The method of exhaustion is typically used to calculate the area or the volume of a figure that is not completely enclosed by straight lines. There are 2 variations of this method, although very similar. We use the example of the calculation of pi to illustrate both variations. We work on a unit circle, so pi is the area of the circle. Firstly, we chop off some smaller regions of the figure and calculate the area of the remaining figure. Then add some of the chopped region back and calculate the new area. This approximation should be closer. Then we can repeat the process as many times as we want to get as close an approximation as desired. This is basically identical to the modern definition of a limit of a sequence, just not written explicitly in modern notations. The second variation is to add something to the intended figure and calculate its area. Then chop some of the added regions and calculate the area again. So in this variation, we approach pi from above as opposed to the previous method, which approaches pi from below. Although it sounds like it acts only as a tool to calculate the area of a curved figure, more importantly, it is used to define the area of such a figure in the ancient times. What Archimedes did was to calculate the area enclosed by a parabola and a line, which is called a parabolic segment. In this video, we are recreating what Archimedes would do if he were to calculate this integral, which means the area of the yellow region. It would be beneficial to reflect this area across the x-axis due to reasons explained later. Archimedes' work was to calculate the red region, but we can see that these 2 areas add up to a triangle, and so to get the value of the integral, we just have to subtract the red region, which is what Archimedes' work was all about, from the area of the triangle. Archimedes' method of exhaustion on a parabolic segment starts off with a novel way to calculate the area of the triangle. We first cut the triangle vertically into 2 different triangles. Regarding h as the base of the 2 triangles, then the corresponding heights would be these horizontal lengths, and so we have this expression as the area. If we now denote s as the sum of the horizontal heights, then we have a simplified formula of the area of the triangle. Here, h can be thought of as the vertical height, and s can be thought of as the horizontal span. Things will be getting more complicated, so feel free to pause the video at any point from now on. The overall idea is to first inscribe a triangle in a parabolic segment. This triangle should have the x-coordinates of its vertices evenly spread out. More precisely, the vertex in the middle should have x-coordinate as the average of the other 2. Then we add the orange areas. Again, the middle vertex is not chosen at random, and it should have the x-coordinate as the average of the other 2. Then we repeat this process indefinitely. The amazing thing about this method of exhaustion is that if we denote the area of the largest triangle as A, then the sum of the orange areas would be a quarter of A. Then the sum of the yellow areas would be a quarter of that of the orange ones, which means 1/16 of A, and so on. So if we know the value of A, we should know the area of the entire parabolic segment. But now we want to figure out why these orange areas sum up to a quarter of A. To explain that, we use physics and treat the parabola as the trajectory of an object flying through the air under gravity. In physics, we usually analyze the projectile motion by separating the velocity vector into its horizontal and vertical components. Here, the blue component does not change, while the green component changes at a constant rate. then this yellow vector represents the average direction the object travels throughout the journey. Since the green component changes uniformly with time, while the horizontal component doesn't change, the average throughout the journey happens midway. This means this yellow average velocity vector should be the same as this red velocity vector midway through the journey. This implies that the red tangent and the yellow line are parallel. Notice that this point is the third vertex when we draw the largest inscribed triangle. Now consider the orange triangle and the lengths of these two yellow lines. Think of this red line as the trajectory of the object if gravity suddenly disappears. Then any vertical difference between the red line and the white parabola should be caused by gravity only. And in physics, we have this equation of motion, which is applicable here because there is no difference in velocity initially. This equation means the vertical distance between the red line and the white parabola is proportional to the time elapsed squared. In this specific case, the time elapsed during these two intervals are the same, so the ratio between the lengths of the yellow lines would be 1:4 because of this squaring proportionality. Finally, we just need to realize this pair of similar triangles. Then this length here should be half that of 4 times L, and we previously discussed that this length is L, which means the vertical height of the orange triangle is of length L. The vertical height of the red triangle is 4 times L because the yellow and red lines are parallel. And by construction, if the horizontal span of the red triangle is 2 times W, the horizontal span of the orange triangle would be W. As a summary, the orange triangle has a quarter of the vertical height and a half of the horizontal span compared with the red triangle. Thus, the area of the orange triangle is an eighth that of the red triangle. By running the same argument on the other side, the other orange triangle would also have an eighth of the area of the red triangle, and so the total area of the orange triangles would be a quarter that of the red one. Running a similar argument, the total of the yellow areas would be a quarter of the total of the orange areas, and so on. So the area of the parabolic segment is A times an infinite geometric series with 1 as the first term and a quarter as the common ratio. But for this geometric series, we have an elegant method to deduce the sum. In this diagram, the side length of the largest square is 2. Then the largest red square should have area 1. Then the second largest have area of a quarter, and so on. Since the two yellow parts and the red part are identical in area, and the area of the whole square is 4, the red part has area 1/3 of the entire figure, which means the geometric series sums up to 4/3. That means the area of the parabolic segment is 4/3 that of the largest inscribed triangle. Recall why we have to do all these. It's for the integral of x squared from 0 to 1. Since both the horizontal base and the vertical height are 1, the area of the triangle formed should be 1/2. And for the red parabolic segment, it would be 4/3 that of the orange area. We know the area of the triangle can be calculated using this formula as discussed earlier. The vertical height of this triangle is a quarter deduced from the difference in these two coordinates, while the horizontal span is simply 1. So we can calculate this expression and obtain the answer as 1/3. The reason why we reflected the parabola so that it opens downwards is to allow physical intuition, which we have used extensively to arrive at this result. The parabolic segment area calculation is based on a treatise by Archimedes called Quadrature of the Parabola, and I have drastically simplified Archimedes' work because his work did not rely on physics or vectors, but purely geometric. If you want to see his work in its full glory, I'll put a link in the description. If you enjoyed this video, give it a thumbs up, don't forget to leave a comment and subscribe to Mathemaniac with notifications on. See you on the next video. Bye!